Right, good afternoon, and thank you for Dave Talbot and the rest of the team for making this conference happen and for inviting me to speak here today. It's certainly an honour to be here as a long-standing supporter of the Thunderbolts project and Plasma Universe generally, and I'm hoping that what I will say today will be able to make a contribution to the ongoing development of the electric universe model, which Wal Thornhill and Monty Childs referred to this morning. So, here we go. As we've seen, the electrical nature of the Sun is not in doubt, but I would suggest that some of the recent evidence doesn't seem to fit our current model. I want to look at this anomalous evidence and speculate on possible changes to the model to account for it. The basis of the EU model is the work of Hannes Alfvén and Ralph Jurgens, who both argued that electric currents are important in the solar system, but they both had differing views on where those currents flow. Alfvén suggested that the heliospheric current sheet is part of a circuit in the heliosphere. Near the Sun, the current splits into north and south components, which then flow along the meridians towards the poles of the Sun. Birkeland currents then flow from each pole, and the Alfvén circuit closes at some unspecified distance from the Sun. The important thing is that Alfvén's current does not enter or leave the photosphere, and the direction of the current changes in alternate solar cycles. Now, in contrast, Jurgens argued that the photosphere is a region of anode tufting, and therefore current must always be flowing through the photosphere into the body of the Sun, which he identified as the anode. By equating the Sun's radiant output to the electrical power and assuming a driving potential of 10 billion volts, Jurgens calculated that the inflowing current is around 4 times 10 to the 16 amps. And according to this model, the anode Sun receives charge which will tend to neutralize it. Now, a potential of 10 billion volts, if it was on the surface of the Sun, equates to a minimum charge of about 3/4 billion coulombs on the Sun itself, which is a very large charge to have accumulated, but it's tiny compared to the inflowing current. And that means the Sun would be discharged in a very short time. Now, Jurgens recognized this and originally postulated that the galaxy's potential kept changing to maintain the voltage differential between the anode Sun and the galaxy. But by 1979, Jurgens and Earl Milton between them had developed a different model in which electrons are simultaneously flowing in through the tufts in the photosphere and out again between them. But they still recognized that you had to deal with this question of how the Sun doesn't get discharged. The current EU model modifies that again, and we now assume that the inflowing electron current is balanced by positive discharges from the coronal torus to the photosphere. And as Wal Thornhill said this morning, these discharges appear as sunspots in the photosphere. In the heliosphere, the inflowing electron current powering the Sun is assumed to drift slowly towards the Sun under the influence of a very low electric field, like the current in a Crookes tube. And the Crookes tube is a device for studying electricity in plasma in the lab. In the revised Jurgens model, the heliopause is assumed to be a virtual cathode where most of the voltage drop occurs. Now, there seem to me to be two questions relating to this model. The first question is how we reconcile Jurgens and Alfvén's circuits. One involves a current flowing in through the photosphere and the other does not. So, Don Scott's diagram, which we saw earlier, combines the two ideas and shows the Alfvén current entering the photosphere at the poles and leaving at the equator. Therefore, given that the photosphere is presumed to be a region of anode tufting, one region should show anode tufting, where the electron current enters, but the other region should not. But what I find puzzling is that the photosphere completely encircles the Sun. There doesn't appear to be any difference between the polar regions and the equatorial regions, suggesting that the current doesn't enter the photosphere and leave the photosphere in quite the way the diagram suggests. So that's one puzzle. The second question is whether the evidence supports the model, And as I said, some of it seems to contradict Jurgen's anode sun, and I want to focus on that first. We've seen that the balancing positive charge is apparently delivered from the coronal torus and creates sunspots as it punches through the photosphere. But there's a puzzle here too. The torus forms at solar minimum, where there are no sunspots, and disappears at solar maximum, as you see on the right, where sunspots are most numerous. Now, these two diagrams I'm showing you here are both looking in the equatorial plane, so they're not the same views as we saw this morning, where the encircling photosphere, coronal torus diagram, was a view from the poles. These are both photographs taken from the Earth, so they're in the equatorial plane. The one on the left is at sunspot minimum, and the one on the right is at sunspot maximum. So the torus comes and goes with the cycle. And the model that suggests that the sunspots are caused by discharges from the torus, it's out of step with when the torus is actually there. Now, another problem is that the source of the balancing positive charge isn't explained. Presumably, protons must come in from intergalactic space along with the electrons, otherwise the heliosphere would become negatively charged. But protons entering the heliosphere seem to contradict the anode model. If we now turn to the evidence for the Jurgen's drift current, to get a current at all, there needs to be an electron drift relative to the positive ions. And we can estimate the relative velocity of the electrons from their known density and the current we need to generate. Now, if all the electrons present at 1 AU radius, that's the radius of the Earth's orbit, if all the electrons are drifting slowly towards the Sun, they've got to have an average drift velocity of 350 kilometers a second to generate the current. And that's almost the speed of the slow solar wind away from the Sun. Now, I would have thought that velocity should be obvious in the spacecraft data, but it's very difficult to find it in the published papers. The measured data seem to indicate that both the protons and the electrons in the solar wind receive additional energy as they get further from the Sun. They're always getting faster. So the protons are behaving as expected, but not the electrons. And we'll look at one or two examples from the literature to show this. Here's the data for electron temperatures from Phillips 1995. The bottom black line shows the expected adiabatic expansion temperature in the mainstream model. The other coloured lines show the electron temperatures as actually measured by various different missions relative to a nominal value of 1 at 1 AU, just to show the shape of the curve. And all the other lines show that the electron temperature is decreasing more slowly with distance than expected. So something appears to be heating the electrons as they get further from the Sun. And that's the wrong way round for an anode sun model. This plot from Cranmer, 2009, shows proton and electron temperatures in the fast solar wind plotted against radial distance, data taken from the Helios and Ulysses missions. The red dots show the protons and the blue dots show the electrons. Strangely, the electron temperature branches beyond about 2 AU radius. The lower values clustered near the black curve occurred at solar minimum, but the uptick of blue points you can see there occurs at solar maximum. And that shouldn't occur if the electrons are being accelerated by an anode sun, and nor should the effect be dependent on the solar cycle. So let's look at the electrons in more detail. Sterbatch 2012 tells us the electron velocity distribution functions observed in the solar wind typically exhibit 3 different components: a core, a halo, and a strahl population. The strahl appears as a beam-like population moving away from the Sun along the magnetic field. Now, in the figure, the strahl population is the white zone under the starred curve to the right here. And the thermal core is a normal Maxwell distribution. The non-thermal halo populations are symmetrically distributed non-Maxwellian distributions. The important point is that there is no corresponding strahl population on the left of the diagram, which is the part moving towards the Sun. As you can see from the velocity at the bottom is 0 in the middle. So these ones are moving away, there are no strahl electrons moving towards the sun over there. And that seems to be clear evidence that there are more electrons moving away from the sun faster than the protons, because the baseline for these measurements is the protons. So taken together, these various strands of evidence seem to argue against an anode sun. So when I got this far, looking for this evidence, which I was expecting to find and couldn't find, I then thought, well, what evidence did Jurgens have? So I went back to his 1972 paper, the original one in which he postulated the anode sun model. And he started off by saying the dipole component of the solar magnetic field can only be attributed to the rotation of the charged sun as a whole, as Dr. Velikovsky pointed out more than 2 decades ago. The problem here is that the dipole field of the sun reverses every cycle, but the rotation doesn't. So that was a puzzle. Jurgens then refers to a paper by Ogilvy, apparently suggesting that electrons in the solar wind are travelling away from the sun too slowly. And I've looked at the original Ogilvy paper, and this is what it says. Ogilvy did find that the electron heat flux values are sufficiently low to require modifications to the Spitzer-Hahn conductivity formula used in the Parker disk model. But he also concluded a detector measures a net electron flux away from the solar direction. Jurgens then quoted a paper by Lemaire and Scherer, who Jurgens says have a solar wind model that claims better than average success in squaring predictions with observations. So what did they say? Their conclusion was that a voltage drop of only 400 volts at around 6 solar radii was all that was needed to explain the observations. And that doesn't sound like a 10 billion volt anode. Jurgens then quoted a paper by Gosling, which he claimed showed the constancy of the solar wind during the solar cycle, arguing that this demonstrated that the energy could not come from inside the sun, otherwise sunspot activity would alter the output. Now, Gosling's paper did say that the average speed was remarkably constant, but he also stated high speeds in excess of 550 kilometers a second were more commonly observed near solar minimum than solar maximum. And Gosling also demonstrated a very good correlation between sunspot activity, the electron corona radiance, and the radio flux. So the sun's output does vary with the solar cycle after all. Which means I find it hard to understand how Jurgens interpreted the evidence that he quoted as support for a 10 billion volt anode sun. Now, I must re-emphasize that the EU model now says that the main voltage drop occurs at the heliopause, not at the sun itself. Now, it is an important change, but it doesn't get round the fact that a 350 kilometers a second electron drift towards an anode sun is needed to power the radiant output in the Jurgens model. Neither does it solve the problem of fast strahl electrons coming away from the sun, or the electron heating further out. And nor does it solve the problem of where the supposed balancing charge is supposed to come from. So altogether, I wonder, are we trying to modify a theory that was flawed from the start? So let's look at what the evidence does actually tell us. The solar wind seems to be evidence of electrical activity, that's clear. But we need to be clear exactly what it is and where it's occurring. The solar wind itself consists mainly of protons and electrons streaming away from the sun. The slow solar wind comes from the equatorial regions where the magnetic field lines of the sun are often looped back into the sun. So we see that in coronal mass ejections and similar formations which loop back in. The fast solar wind comes from the higher solar latitudes, and especially at solar minima, where coronal holes appear as dark regions in the X-ray spectrum you can see on the right here. After leaving the sun, the fast solar wind curves along the magnetic field lines towards the equator from both poles, eventually linking up to form the heliospheric current sheet. And this diagram from Cole's 1998 paper shows the effect close into the sun. A little bit further out, you'd have seen the lines coming from the poles also dropping down onto the equator. Now, this geometry is similar to the geometry of the Alfvén current. except that it's not clear there's a concentration of current along the polar axes. The situation seems to me to be more like the proton emission in the Cigar Galaxy shown in the picture on the right, where the protons are the red explosion vaguely along the axes, but not concentrated on the axes. So the question is, what accelerates the solar wind? Is it a small electric field through the heliosphere, or is it more local to the sun? There's evidence that the acceleration takes place very close to the sun in astronomical terms, and I'll just give you two examples from many in the literature. Shapiro in 2012 states the solar wind acceleration region is a dozen solar radii. And Frasin in 2003 states we know that the O5+ ions need to accelerate somewhere before 0.3 AU. These and many similar references appear to suggest that the acceleration zone is close to the sun and not spread throughout the heliosphere. So let's look at the field that the EU model predicts. Now, Walthorn-Hill has made the point that simple electrostatics can't be applied to the Crookes tube discharge model of the heliosphere. The pithball model on the lower picture is the wrong model. I agree. The Crookes tube analogy suggests that there's no space charge in the heliosphere, but there is a shell of positive charge at the inner boundary of the heliopause, which maintains the sun's potential up to the heliopause. And outside this positive layer, there's a negative layer, which is the virtual cathode, where most of the potential drop occurs. And in the model, the electric field from the anode sun itself will fall off with the inverse square of the distance from the sun, giving a low electric field within the heliopause as required, but a high electric field immediately adjacent to the sun. If you've got a charge on the sun, there must be an electric field coming from the body of the sun itself, and then outside that you have the heliopause double layer where the main drop occurs. But we can't get away from the fact that you need a potential drop near the sun. And this makes the anode sun behave like a double layer, exactly as we've seen in the acceleration data. So far that's so good, but it's more complicated than that. Because in the EU model, there are actually 4 separate charged regions. The body of the sun is an anode, and in this diagram, the body of the sun is off to the left here, and its anode voltage is this intersection with that axis on the left. The inner and outer photospheres are 2 layers of positive charge, which you can see as blue regions here, causing the height of this potential hill here. And then the lower corona is a negative layer here, which causes this steep potential drop down here. As we've just seen from the data appears to indicate that the acceleration is coming from this steep potential drop here, as the model suggests. But the acceleration data, which is what we measure way out here somewhere, can be explained by this part here. How do we know from the data that you've got this extra layer here and you've got an anode sun here? I find it hard to see how we can interpret from measurements out here what's going on behind this double layer here. So we've got no direct evidence of the anode sun inside that steep double layer. Apart from causing the charge layers out of the heliopause, there appear to be 2 main reasons why the anode sun body is necessary. And the first is to drive the inflowing current from galactic space and to power the sun. In a Crookes tube, the current is driven by the external circuit, and that also removes any charge arriving at the anode, so you don't have a charge balancing problem. The second reason for having an anode sun relates to the control of the solar wind by Don Scott's PNP transistor analogy. And that model assumes that the ions in the anode sun are trying to escape, and so they need to be restrained by this potential hill here in the photosphere. And alteration of the height of this hill here regulates the amount of ions that are allowed to pass across and reach this steep part here, the double layer, and that controls the output of the double layer, which we measure out here as the solar wind. Now, without an anode sun, an outwardly directing double layer consisting of the outer photosphere and lower corona would accelerate the positive ions in exactly the way we measure. But then how could the control work if you don't have this hill part between the anode and the inner photosphere? Well, in the first place, without an anode, there is no excess of positive ions trying to escape. Any positive ions that are drifting around here will be accelerated if they get to the edge of this hill, and they'll be accelerated down the potential hill if they approach the double layer, but they won't be being forced outwards from an anode sun if it isn't an anode. And secondly, control of the acceleration is basically the control of the height of this part of the hill here. And that could be achieved equally well either by the adjustment of the voltage of the photosphere here, that is the amount of charge in these layers, or, slightly more subtly, you could keep the charge in the two layers the same and simply separate them, physically separate them slightly further. And both mechanisms would increase the voltage, or therefore the height of the hill, and therefore the acceleration. So just this part, the double layer part here alone, can provide the control mechanism. So I wonder, is an anode sun necessary after all? So if there's a double layer without an anode sun inside it, what happens at sunspots? The transistor analogy suggests that sunspots are holes in the double layer through which the positive ions can leak out. But a problem with this model is that the observed motions of sunspots appears to show that matter is falling in. For example, Newton in 1958 refers to an always present slight downdraft of hydrogen and calcium gas from the chromosphere above a sunspot, falling in. Also, sunspots are known to emit electrons. We've already seen Birkeland's work presented a couple of times this morning. Here's the diagram you'll recognize. Now, in relation to this diagram, Birkeland refers to the emission of cathode rays from sunspots and compares them to what he found when his Torella was the cathode, not the anode. With slight magnetization on his cathode globe, the rays came from the equatorial regions, which is the sunspot belt, and they formed groups, exactly like sunspots do, as we see here in the picture. And these rays, these cathode rays in Birkeland's Torella, seem to be analogous to the Strahl electron beams we've already seen. In his recent interview with Michael Goodspeed, Don Scott pointed out the correlation between sunspots in the photosphere and the bright X-ray emission regions in the chromosphere and corona above. The X-ray emission stops at higher latitudes where there are no sunspots. Now, X-rays are due to high-speed electrons impacting neutral atoms. So it seems that the high-temperature electrons causing the X-rays are coming from the sunspots. These factors all seem to point to a source of high-energy electrons inside the sun, which need to be contained by the double layer, in contrast to the containment of positive ions in an anode sun. The double layer would be the same way around we've seen already, but it's just containing electrons, not protons. So why should there be a double layer at all if there's no anode body there to cause it? It's well known that plasma also forms a double layer to separate areas of plasma with different properties, such as temperature or degree of ionization. And these types of double layer are current-free double layers in contrast to the current-carrying double layers formed in a Crookes tube. And in essence, that's the difference I'm suggesting. The anode sun model requires a CCDL around it, but plasma could generate a CFDL cell boundary without a charged anode. And the particle acceleration in the double layer is similar in both cases, but one type of double layer is caused by an externally driven current, and the other is not. So perhaps we should look at what sort of plasma the sun might contain, which would prompt the formation of a current-free double layer. The recent interest in cold fusion has led to the study of plasmoids, and this is an example here. I'll show you. I'll have a small drink. Most cold fusion devices aim to create a high-temperature plasma which is contained by external magnetic fields, such as seen here in the tokamak machine near Oxford. However, there's a perfectly good example of naturally occurring self-contained plasmoids in nature, and that is ball lightning. And the recent cold fusion research has looked at ball lightning in an attempt to explain what's going on in these lab machines. I found two very good papers by Tsui, published in 2001 and 2003 respectively, who demonstrated that there's a stable, force-free arrangement of currents in a plasmoid when there is the right balance of toroidal and poloidal fields. So that means that a stable plasmoid is like a Birkeland current wrapped around into a closed loop. And this force-free form occurs at all scales. It's been suggested elsewhere that the electron itself is a toroid. And as we heard this morning, Wald Thornhill has argued that there's a plasmoid at the heart of the Milky Way and other galaxies. So if we accept that, it seems possible that a plasmoid may be contained inside the Sun and other stars as well. Now, this idea isn't new. Alfvén argued that the Sun was a pair of toroidal rings. And this double ring model explains the loops of prominences on the Sun as escapes from the toroids. And perhaps that's why the Paris Observatory recently published a similar image seen on the right. Something of an artist's impression, but at least they're adopting the model. Now, Bostick's experiments in 1956 demonstrated that the rings are formed when a plasma gun discharges into a magnetic field across the field lines, as you see on the left. Initially, the plasmoids are tubular and aligned along the field lines, and they then develop into knots and eventually into rings. In contrast, shown on the right, Charles Bruce was convinced that ball lightning is a result of ejection of plasma from bends in lightning discharge channels, where the stretched magnetic field allows highly energetic plasma to escape from the main lightning discharge channel. And observations of naturally occurring ball lightning seem to support this view that it's associated with conventional lightning discharges. And Birkeland currents can also develop bends due to what is known as the kink instability. So a plasmoid could be formed at a kink instability in a galactic Birkeland current without the need for an artificial plasma gun. Now, if a star forms as a plasmoid, it will inevitably contain high-temperature electrons, similar to the tokamak devices, and so we should expect to see FDL to form around it to separate the two plasma states. So, I'd like to suggest that there may be a plasmoid in the centre of the Sun and a CFDL around it. Ionization would then occur in the interaction region with the surrounding plasma. The tufting in the photosphere would be due to ions being accelerated away because they've got too close to the double layer, and electrons would be drawn in against the electron temperature gradient. And sunspots in that case would be leaks of high temperature electrons, like the Birkeland experiments, and the leak of high temperature electrons would maintain the overall neutrality of the plasmoid. The energy would come from the energy contained in the plasmoid, which is slowly leaking out via interaction with its environment, which is similar to what we see in ball lightning behavior. And the CFDL would accelerate the solar wind away from the Sun, just like the CCDL in the anode-Sun model. But the plasmoid Sun CFDL model avoids the problems of the electrons not behaving further out, and it also avoids the need for a balancing proton inflow into an anode Sun. So it solves a couple of problems. But if we replace the anode Sun with a plasmoid Sun, where does this leave the Alfvén current? Well, I suggest it leaves it exactly where it was, with the one exception that we touched on earlier. The concentration of the current along the polar axis is not obvious in the Ulysses mission data. It seems to be more distributed, and therefore more like the arrangement shown here from Alfvén's 1941 paper. In that paper, he argued that the field-aligned currents from the Sun cause orbital rotation of the heliospheric current sheet by the Faraday motor mechanism. It seems as though the Alfvén current around a plasmoid which is not energetically producing axial jets is primarily concerned with rotation and transfer of momentum, not with the processes going on in the photosphere itself. But if that's so, which way is the momentum being transferred? Recent evidence suggests that the corona is not rotating the same way as the photosphere, or in the same way. rotates in the same direction, but not in the same manner. This graph from Giordano, 2008, shows the measurements of the rotation period plotted against latitude. And the parabolic curve shows the differential rotation of the photosphere for comparison. And the puzzling aspect is that the corona does not show differential rotation. Also, the corona has a faster rotation, that is a smaller period, than the photosphere at higher latitudes. So that says to me that the photosphere can't be driving the corona. It seems that it's the corona that's linked to the Alfvén's Faraday motor. But Alfvén's mechanism can work both ways, and therefore it's possible that the corona can be driven by the heliospheric current sheet. But if so, where could the heliospheric current sheet motion come from? The recent evidence from the IBEX mission suggests that the heliosphere sits in the centre of a galactic Birkeland current. And it seems reasonable to assume that the presence of the heliosphere affects the Birkeland current, which either bulges around it, as NASA says, shown on the left, or perhaps pinches down onto it, as we might prefer. Now, we know that a Birkeland current has a radially varying helicity, which allows each particle to follow the magnetic field line at its own location. The balance is maintained automatically because if I is not parallel to B at any location, the cross product will generate a radial force which moves the plasma back into alignment. So suppose that the heliosphere causes the Birkeland current to become misaligned at the bulge or the pinch, then some plasma will be shifted radially into or out of the heliosphere. If it's incoming, it will still be carrying the spiraling current, which is carried mainly by the electrons. So the incoming electrons will have a strong orbital velocity component and an inward radial drift, in which the electrons are moving faster than the protons. Once inside the heliosphere, we would see this as the current in the heliospheric current sheet, which, according to Alfvén, spirals in towards the Sun in alternate cycles. The motion of the heliospheric current sheet could then drive the corona by the Alfvén mechanism in reverse. During the other cycle, when the Sun's magnetic field is reversed but the rotation remains the same, the radial component of the current must reverse and flow back out. And it may be during that phase the corona is driving the heliospheric current sheet. So it seems possible that the solar cycle is due to the galactic current bleeding into the solar system in one cycle and leaking back out again in the next. And Don Scott has recently referred to a paper by Decker published in Nature in September 2012. Decker reported that, contrary to NASA's models, Voyager 1 had measured 0 north-south plasma flow near the heliopause. And instead, they found an unexpected, totally unexpected, east-west ion flow, plus a continued radial drift. So already there seems to be some evidence for the suggested interaction of the heliosphere and the Birkeland current. So to summarize, I suggest that the evidence does not seem to support Jurgen's anode sun, but it's more in favor of a CFDL near the Sun. And this may be a result of normal plasma cell formation around a force-free plasmoid, which could have been formed by a discharge from a kink instability in the original galactic Birkeland current. The energy would come from the plasmoid, similar to ball lightning, and cause ionization of the plasma next to it. The DL accelerates the ions and draws in electrons until there's an imbalance, when high-temperature electrons escape via holes in the DL, which we see as sunspots. The role of the Alfvén circuit seems to be largely rotational, transferring momentum between the corona and the HCS, and exchanging electromagnetic and kinetic energy during the solar cycles. The coronal torus does store part of that energy during the cycle. The primary driver for coronal rotation may then be the galactic Birkeland current bleeding into the heliopause due to misalignment at a pinch or bulge around the heliosphere. And oscillations of the misalignment might cause the solar cycle. But is it right? I don't know. We need more evidence. But I do suggest that the forthcoming SAPPHIRE experiment should keep an open mind as to whether the Sun is an anode or not. And I think the Thunderbolts project either has to find convincing evidence for a drift current towards the Sun and a better means of maintaining the anode voltage, or perhaps we have to consider abandoning the anode Sun. Electricity is undoubtedly the key, but how and where it flows is uncertain. I mean, the good news is there's still plenty of physics to be sorted out, and I think it's exciting to be involved in the search for answers. I hope you agree, because there's a role here for anyone who's interested. Thank you for listening.